This is the title of the quiz question. It's about understanding how a technique called shrunk covariance works to improve estimates of covariance matrices. Think of it like this. We're trying to create a better picture of how different financial factors for companies relate to each other. The quiz focuses on this method, particularly in scikit-learn, a popular Python library for machine learning. Here, the problem is introduced. You have data on companies' finances, and you want to understand the relationships between different financial indicators. The question points out a common issue. Directly calculating the covariance matrix from limited data often gives unreliable results. The quiz problem introduces a solution using the _shrunk_covariance function. This highlights the core issue. If you only have a few data points, your calculation of the relationship between different financial values may be far from accurate. The limited sample size makes the standard covariance calculation unreliable. This is where the _shrunk_covariance method comes in to give a better approximation. This section indicates that the question will be multiple choice. You will select the correct statements about _shrunk_covariance. This sets the stage for the multiple choice questions that follow. The focus is on understanding the properties of the _shrunk_covariance function within the scikit-learn library in Python. This is the first multiple choice option. It asks whether _shrunk_covariance always ensures the resulting matrix is positive semi-definite. This is a crucial mathematical property for a valid covariance matrix. This is the second option. It checks if the Ledwall-Wolff method is the only way _shrunk_covariance achieves optimal shrinkage. Ledwall-Wolff is a particular technique for improving covariance matrix estimates, but the statement questions if it is the exclusive method in _shrunk_covariance. This is the third option. It explores the range of values the shrinkage parameter can take. The shrinkage parameter controls how much the original covariance matrix is adjusted. It's a crucial element in understanding _shrunk_covariance operation. The fourth option examines the effect of increasing the shrinkage parameter on the accuracy of the covariance estimate. It's important to understand that while shrinkage helps, excessive shrinkage can actually make the estimate worse. Hey Vamsi, we're dealing with a problem where the sample size is too small to reliably calculate a covariance matrix. A covariance matrix shows how different variables in a dataset change together. A small sample size means the calculated matrix might be inaccurate, leading to unreliable conclusions. This is a common issue in statistics, and we need a better solution. To fix the unreliable covariance matrix issue, we'll use a clever function from a Python library called scikit-learn. This function, called _shrunk_covariance helps improve the covariance matrix estimate. It does this by adding a bit of shrinkage. Essentially, it makes the estimate less sensitive to random fluctuations caused by the small sample size. It's like smoothing out the bumps in a rough road to make the journey smoother and safer. Now, let's test your understanding. Here's a multiple choice quiz about _shrunk_covariance. Are you ready to put your knowledge to the test? This question is asking you to identify true statements about the _shrunk_covariance function. It tests your understanding of its core functionality, how it works, and what it can and cannot do. Pay close attention to each statement and select those that accurately reflect the function's properties. The _shrunk_covariance function in scikit-learn takes several parameters. This row highlights the crucial one. _shrinkage. This parameter controls how much the sample covariance matrix is modified, shrunk, towards a simpler structure. It's a crucial tuning knob that balances the trade-off between reducing the impact of noise and preserving true covariance relationships. The _shrinkage parameter is a value between 0 and 1, inclusive. A value of 0 means no shrinkage is applied. The function returns the original sample covariance matrix. A value of 1 means maximum shrinkage. The function returns a highly simplified covariance matrix. Intermediate values represent partial shrinkage, a compromise between these extremes. This parameter is essential for adjusting the strength of the shrinkage effect. finding the optimal balance between noise reduction and information preservation. This is the input to the shrunk_covariance function. It's a matrix that represents the relationships between different variables, e.g., financial indicators, in the dataset. Calculating this directly from a small dataset can lead to unreliable results. High variance estimates of the covariance matrix is likely to occur. The function aims to improve the quality of this initial estimate using a shrinkage process. This is the output of the shrunk_covariance function. It's an improved estimate of the covariance matrix obtained by applying the specified shrinkage intensity, the shrinkage parameter, to the input sample covariance matrix. Crucially, this output matrix is always positive semi-definite, ensuring that variances are non-negative and enabling meaningful statistical interpretations, unlike the potentially unreliable input sample covariance. This refers to the Ledwall-Wolff shrinkage method. This is an advanced technique for calculating the optimal shrinkage intensity. Instead of manually setting the shrinkage parameter, the function can automatically compute the ideal value based on the input data. While optional, this method often produces more reliable results than manually tuning the shrinkage parameter. It's a convenient and sophisticated way to improve covariance estimation in datasets with small sample sizes. This is the title of the quiz question, introducing the topic of using the shrunk_covariance function in scikit-learn to handle unreliable covariance matrices from small datasets. This statement asserts that the shrunk_covariance function always generates a positive semi-definite covariance matrix. A positive semi-definite matrix is a crucial property for a valid covariance matrix, ensuring non-negative variances. The function's design guarantees this property, making statement a true. This statement claims that the shrunk_covariance function exclusively uses the Ledwall-Wolff method for determining the optimal shrinkage intensity. However, while Ledwall-Wolff is a common and often default method, the function offers flexibility and allows for directly specifying the shrinkage intensity. Thus, statement B is incorrect. The statement correctly describes the valid range for the shrinkage parameter within the shrunk_covariance function. A value of 0 indicates no shrinkage, using the sample covariance directly, while 1 represents complete shrinkage, using a highly simplified covariance structure. Values outside this range are not permissible, making statement C true. This statement suggests a direct positive correlation between increasing the shrinkage parameter and the accuracy of the covariance estimate. However, excessive shrinkage can lead to oversimplification, losing important information from the sample covariance. The optimal shrinkage intensity is data-dependent, making statement D false. This quiz question focuses on understanding the scikit-learn's shrunk_covariance function, which is used to estimate covariance matrices more reliably, especially when dealing with limited data. It tests knowledge about the function's properties and how its parameters affect the outcome. Think of it like this: we're trying to get a better picture of how different aspects of a company's finances relate to each other, but our data might not be complete enough. This function helps us make a smarter guess. The question presents 4 statements about the behavior of the shrunk_covariance function and asks to identify which ones are true. Each statement will be analyzed individually to determine its validity. This is a typical multiple-choice question testing your understanding of the function's properties. Statement A claims that shrunk_covariance always produces a positive semi-definite covariance matrix. A positive semi-definite matrix is a requirement for a valid covariance matrix. It ensures that variances, which represent the spread of data, are not negative, which would be nonsensical. The shrunk_covariance function guarantees this property, making the statement true. Statement B states that shrunk_covariance only uses the Ledwall-Wolff shrinkage method. While Ledwall-Wolff is a popular method for calculating the optimal shrinkage intensity, shrunk_covariance also allows for manually specifying the shrinkage parameter. Therefore, this statement is false. Statement C says that the shrinkage intensity parameter, often called shrinkage, must be between 0 and 1. A. Shrinkage. Value of 0 means no shrinkage, using the sample covariance as is, while a value of 1 means maximum shrinkage, using a simplified covariance structure. Values outside this range are not valid, therefore, statement C is true. Statement D claims that increasing the shrinkage parameter always improves the accuracy of the covariance estimate. This is false. Too much shrinkage can oversimplify the covariance structure, discarding valuable information and reducing accuracy. The optimal amount of shrinkage depends on the specific data. This row describes the overall process of using the shrunk_covariance function. It takes financial data, represented as a covariance matrix, as input, applies shrinkage using a specified parameter between 0 and 1, and produces a positive semi-definite covariance matrix as output. This summarizes the function's core workflow. The input to the shrunk_covariance function is a covariance matrix derived from financial data. A covariance matrix shows how different financial indicators, e.g., stock prices, revenue, expenses, relate to each other. This refers to the specific function from the scikit-learn library in Python that performs the covariance shrinkage. Scikit-learn is a popular machine learning library. This specifies the degree of shrinkage applied to the covariance matrix. A value of 0 means no adjustment, while 1 represents maximal shrinkage towards a simplified structure. The function's output is a modified covariance matrix that's guaranteed to be positive semi-definite. This ensures the matrix is mathematically valid for further analysis and interpretation.